Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. In the vast, frozen expanse of Antarctica, miles away from human habitation, the ice is not silent. If you were to place ultra-sensitive seismometers onto the frozen crust of a mammoth tabular iceberg, you would record a haunting, continuous acoustic hum. Glaciologists call this phenomenon a glacial harmonic tremor, and it is effectively the sound of an iceberg singing. But far from being a tranquil polar lullaby, this subterranean music is a direct manifestation of violent fluid mechanics and structural strain that dictates the catastrophic collapse of colossal ice shelves. To understand how a billion-ton block of ice produces a sustained musical tone, we have to examine the laws of fluid dynamics and resonance. Think of a classic pipe organ or a flute. When air is forced through a narrowed tube with specific geometry, it produces acoustic vibrations at discrete resonant frequencies. In a singing iceberg, the mechanism is strikingly similar, but instead of breath flowing through brass, high-pressure liquid water surges through an intricate labyrinth of subglacial channels, crevasses, and conduits. During polar summers or under intense tidal pressures, meltwater lakes on the ice surface drain rapidly into deep vertical fissures known as moulins. As this pressurized water collides with narrow constrictions inside the ice, it generates hydromechanical pulses. These pulses cause the elastic ice walls of the crack to flex and oscillate violently. If the velocity of the fluid flow matches the natural mechanical frequency of the ice cavity, resonance occurs. The surrounding ice mass begins to vibrate in unison, generating a sustained, harmonic seismic tremor that can reverberate for days at a time across thousands of square kilometers of ocean and rock. Most of these vibrations occur at low frequencies, often between 0.5 and 5 Hz. Because this sits in the infrasound spectrum, well below the human hearing threshold of 20 Hz, researchers must speed up the seismic recordings by several dozen times to make them audible. When played back, the tremors sound like a cross between a buzzing swarm of mechanical bees and the eerie hum of an untuned cello. Crucially, the pitch of the song is not static. As the internal water pressure fluctuates or as the geometric dimensions of the crevasse shift, the fundamental frequency glides smoothly up and down, mirroring the changing physics within the ice. These harmonic tremors are not merely scientific curiosities, they are the mechanical signatures of structural destruction. The continuous hydraulic hammering responsible for the hum exerts immense tensile stress along the tips of glacial fractures through a process known as hydrofracturing. Liquid water is denser than ice, meaning a water-filled crevasse creates an outward wedge pressure that vastly exceeds the confining strength of the surrounding glacial mass. As the iceberg sings, it is actively driving microcracks deeper into its foundation. When an entire ice shelf, such as the Larsen B or the massive Ross ice shelf, becomes riddled with these resonant hydraulic pathways, its structural integrity decays at an exponential rate. Seismic monitoring stations deployed across the ice can detect changes in the harmonic tremors frequency, providing scientists with an acoustic real-time map of crack propagation. A sudden shift in the vibrational tone often indicates that a major structural bridge inside the ice has ruptured, signaling an imminent calving event where ice blocks the size of small cities tear away into the Southern Ocean. Furthermore, as global ocean temperatures rise, warm seawater erodes the submerged grounding lines of these marine terminating glaciers from below. This basal melting alters the buoyancy balance of the ice shelf, introducing new torsional stresses that trigger distinct acoustic signatures. By decoding the pitch, harmonics, and duration of these subterranean songs, geophysicists can now model exactly when an ice shelf will transition from stable elastic deformation to catastrophic mechanical failure. Listening to the singing icebergs transforms our understanding of polar glaciology. Far from inert, static monuments of cold, these colossal structures are dynamic mechanical systems that groan, vibrate, and chime under the immense forces of fluid pressure and gravitational stress. Tracking their acoustic lives gives us an unprecedented window into the physics that will reshape Earth's coastlines in the centuries ahead. For more incredible facts like this, don't forget to subscribe and turn on notifications.